Good morning, everyone. I welcome you all on behalf of the IIT Alumni Center, Bengaluru, for this 56th webinar. We have been conducting these webinars online since April 2020. It's been a great journey, and you can find our previous webinars on our YouTube channel. It's quite popular, and you'll find a whole range of seminars on various topics. And we normally have these webinars online on Saturdays, typically twice a month at 5 in the evening. It's spearheaded by Dr. Sushila Venkatraman, and she's been the driver for these webinar series. Today we have this special deep dive webinar, actually first time in the morning. So it's quite it's an experiment for us also. So this special deep dive webinar today is being delivered from the faculty at IIT Jodhpur, one of the newer, younger IITs. And the first topic is related to the challenges and opportunities for VLI systems in the intelligent world, which is going to be addressed by Professor Manoj Choudhary, who's at the Electrical Engineering Department. The second topic is on smart camera systems by Dr. Amandeep Kaur, who's an assistant professor in the Electrical Engineering Department at IIT Jodhpur. So very brief introduction about the speakers. Professor Manoj Choudhary is the professor at EE at IIT Jodhpur. He got his PhD from IIT Kanpur in communication system. Professor Manoj has a very vast experience in the industry as a technologist and business leader, working with many top electronic and semiconductor companies such as Samsung, Texas Instruments. Prior to joining IIT Jodhpur, he was the senior director and head of the systems LSI and R&D at Samsung Semiconductor India in Bangalore. So he had led the business unit and grew the team by 5x to a very big organization of nearly 1,200 R&D engineers working on system and chip design and development along with software. So Manoj is quite active, is published quite a bit. He's also co-authored a book on ultra-wideband technologies, and we really look forward to listening to him. And following him, Dr. Amandeep Kaur is who's an assistant professor in EE in IIT Jodhpur. She's an expert on camera systems for high-speed and low-power applications. She did her PhD at IIT Delhi. She also serves as a woman in engineering chair in Vlsi DAT. Her area of interest, research interests includes analog and mixed signal circuit design and intelligent circuits and systems. So we really look forward to listening to both the speakers. A couple of small rules which we follow in these webinars. We have a Q&A box. So we would like the audience and the participants to interact or ask questions via the Q&A box. And Professor Manoj will address these questions after his talk, the first half. And then later on, Dr. Amandeep will look at the Q&A box and address the rest of the questions. So we look forward to an engaging hour of discussion. Over to you, Professor Manoj.
Thank you, Professor Narayanan and the IIT Alumni Center at Bengaluru for organizing this talk. Presenting the talk at this particular juncture is very, very important for India, because India had recently launched the India Semiconductor Mission, and IIT Jodhpur, in tune with the India Semiconductor Mission, is launching an executive MTech program on intelligent VLSI systems, particularly focusing on how the AI world and VLSI world will intersect with each other. Having been associated with industry, my orientation in the talk will be more industry-centric and will also like to give a flavor of how the world is moving, and in particular, where the working professionals can expect to build their careers in future, and how IIT Jodhpur's program in intelligent VLSI systems is a very, very timely step. As you mentioned, IIT Jodhpur is a new IIT. It's in second generation IIT. So we just completed 14 years and had a 15th foundation day. So just like a teenager, which is in its currently in its 15th year, we have a lot of energy, lot of passion, lot of dreams to make bigger things and find our well-deserved place amongst the committee of top international education institutes in the world. So I will begin the talk, and please let me know if you are able to see the slides. So firstly, so the title of the talk is Challenges and Opportunities for VLSI Systems in the Intelligent World. We are too early in the morning, maybe many of us have to hurry up. So let us look at, probably we had a chance to have a coffee. So in the coffee machine, if one looks into that, in such a simple device like coffee machine, there are at least 10 plus semiconductor components. For example, we have temperature proximity level sensors that measures the milk level and the temperature levels and so on. There is a display, so you have a display IC, an audio. There is a power management IC that controls the temperatures. There is a position sensors that determines whether the cup is full or not, and of course the various connectivity. What I try to emphasize here is starting point is semiconductors is everywhere, and the role of semiconductors is increasing in the current ecological ecosystem that we are in. Right, starting from the coffee machine, let us go to a smartphone. Each one of us carry that. There are around 170 semiconductor components in a smartphone, starting with CMOS or CCD camera chips, various image signal processors that improve the quality of the images and the videos we take, GPS modules, power management IC, because in a phone there is only one source of battery, one source of power, which is a battery. Even if you have a 500 milliampere hour, there is only one source. And you have several power requirements. For example, you power on a display, there is a power that is being consumed. If you talk over a phone, there is a power that is being consumed. You browse YouTube channels, YouTube or Netflix, there is a power that is being consumed. You consume data, there is a power being consumed. So there are several power management IC in a phone. You have multiple sensors and therefore controlling them. These days, 4G and 5G modems that allow us the connectivity, RF front-end modules, multitude of sensors like proximity, accelerometer, so on, whether we are charging using a wire or a wireless charging function. Many of the storage components like DRAM, NAND, application processor, of course, is inherent part of any phone. Therefore, what I highlight here is that from coffee machine to smartphone, we actually have significantly increased the complexity in terms of both the quantity of the semiconductor component as well as the complexity of the semiconductor component. Let's move forward. A car of today has approximately up to 3,500 semiconductor components. So car is no more a mechanical device. Today, 40% of automotive's cost is electronics, and primarily semiconductor plays a very big role into that. If you look at LED for lighting, or if you look at, for example, within your cabin, whether the gas is there, there is a humidity sensor for cabin air quality control. We have in-cabin wireless USB charging capabilities these days. We have many power management ICs and automotive ICs that provide and control in-vehicle infotainment systems, or in future also the autonomous driving ADAS systems We have wireless communication chips that will allow, for example, vehicle to everything in vehicle to vehicle communication. We have multitude of sensors in a car related to oil, coolant, voltage, fuel, mass, airflow, engine speed, so on. In future, when we are building the ADAS systems, it will have LiDARs, it will have neural processing units to sense the surroundings. It will have a large memory for the data that various sensors are transmitting and the processing that needs to be done. So for many of the airbags, the pressure sensors and so on. So my intention here is not to talk about each and every sensor. For example, we also have these days cars in India, which have the lane departure warning system. So each of them require not only a sensing capability, which is provided by a semiconductor component. Therefore, the message I want to convey from this slide is from coffee machine to a phone that we carry, coffee machine that we used in the morning for a morning cup of coffee, to a phone that we are carrying, to a car that we are traveled maybe to our respective destination. There is an increasing quantity and complexity of the semiconductor component. And therefore, assuming that the audience is mostly working in the semiconductor area, all I want to emphasize is that the future is very bright. We are into a world where the importance of semiconductor is growing and growing and growing. And therefore, we are in this technology world at the very, very right time when it is growing significantly. Not only the three areas that we talked about, any areas that we today talk, whether it's smart defense using drones, intelligent weapons, or smart cities, which utilizes smart cameras to improve traffic flows, pedestrian safety, and so on, smart home, where multitude of connected devices in the home like refrigerators, washing machine, surveillance video, lighting appliances, or in smart manufacturing in Industry 4.0 scenarios like robot-assisted assembly line monitoring, or predictive maintenance, or production monitoring, or in agriculture like precision crop monitoring, farming drones, smart sensors, smart retail, for example, or in smart mobility like what we talked about, or very importantly in the smart healthcare segment where we recently have been undergoing pandemic, so pandemic compliance control monitoring, or inventory tracking, or precision healthcare, telemedicine, remote basic, all of these sectors, the semiconductor chips are the backbone of the innovation that powers the devices in all of these ecosystems to generate value, to generate outcomes which are needed for each of the sector to perform and each of the sector to excel and deliver innovation that improves human life. So in terms of semiconductor component, we all know that we are, when we talk about chips, we are trying to make semiconductor chips by putting more and more transistors together in them, packaging them more and more. So in this slide, all I am trying to show is the process nodes, which we denote these days in nanometers. Basically, at a very rough level, you can say that that is a distance between two transistors when they are densely packed together. At a very, very crude level, I can mention that. So what we are trying to do, as we try to pack in more and more complexity in the chip, we are trying to have more and more transistors, which are basic elements for any of the computational device. For example, so these days we already have 5 nanometer, 4 nanometer process system on chips that are available in the market. We are already moving to 3 nanometer with increased demand currently from 5G and moving to the newer segments into AI, augmented virtual reality, quantum computing. This journey that we are making and trying to have more and more advanced nodes and more transistors being packed closer to each other in emotion recognition and IoT kind of devices, we are in for exciting times. Now, I come to the same diagram once again, but what different thing I am trying to show here is that not all components in a car, for example, we talked about 3,500 semiconductor components in an automobile, not all components are manufactured using the same technology process or has the same kind of a technology orientation. As we look, we are showing here, many of the components, for example, are manufactured at process nodes which are older, like 180 nanometer, because those kind of requirements can be fulfilled to that. However, many of the wireless communication chips these days are not only 10, but even up to 5 nanometer process. So, though semiconductor components in automotive may be 3,500, there is a requirement for all of us to understand different technology nodes and different design requirements that power each of these requirements within the automotive, and so on. One more thing that has been happening all over is that whenever electronic systems have been made, there has been semiconductor content in them. The semiconductor content over last 20 years has significantly risen and almost have doubled in electronic system. So earlier electronic systems probably had around 18% as a semiconductor content. It is significantly increased to about 30%. So the role of semiconductor in any electronic system has also grown very significantly. If we look at the international roadmap on devices and systems that is produced by IEEE every year, if the 2022 roadmap we look at, we continue to see a very good progress for all the semiconductor across smartphones, PCs, and the automotive segment that we talked about. AI is becoming all pervasive, and artificial intelligence, machine learning, these tools are getting used everywhere. So there are two aspects that one can talk about. One is, what are the chips that power the artificial intelligence? And secondly, what are the artificial intelligence related algorithms that can help in the chip design? So if you merely look at the AI chip market, the chips that are getting used for making systems intelligent, these days everything is intelligent in the sense that you have, wherever you have a word smart inserted, whether it is a smartphone or a smart TV or a smart home, a smart city, smart healthcare, everywhere, wherever you talk about the word smart, there is a kind of a inclusion of intelligence into that. So AI chip market is significantly growing. The chips that power the AI applications, for example, there is a 42% growth of AI chips in automotive segment, in industrial segment, we see a 16%. So the main point that I want to highlight in this particular slide is that as AI, ML, edge computing, and 5G technologies are continuing to gain footing, semiconductor companies are also positioning themselves to take advantage of this opportunity. With IoT applications, basically IoT applications utilize AI, ML, and edge computing significantly, and IoT network is growing. We already have roughly around 27 billion devices connected to IoT, and it is growing rapidly. Therefore, the trend for semiconductor chips to include more of AI, as well as the usage of AI more and more into the semiconductor chip design, is going to increase even further. This is a very classic slide. Whenever the logic transistor, the basis of today's semiconductor revolution started long before. As we noticed, this is a slide from Intel. We are moving from planar to FinFET technologies to the newer and newer processing technologies to power 3 nanometer and so on. Memory, an important component in semiconductor design, when we put logic and memory together, memory is also expected to significantly go from current versions to around 1000 bits in generation 14 by 2030. So we can see that the current levels that we have, 170 layers, will go to approximately 7 or 8 times over the next 7 or 8 years. It is in this context that there is a growing need of semiconductor all around the world, which is increasing. There is a growing and emerging trend of artificial intelligence-based systems that are evolving, and therefore an intersection of AI being used in the VLSI system designs, or the newer VLSI systems designs being designed to help AI applications. It is at this cross junction that IIT Jodhpur is launching its executive MTech program in the intelligent VLSI systems. The main theme is, in the current era of IoT, AI, and 5G, there are multiple prototypes that are being proposed and demonstrated for smart and real-time applications that we talked about. For supporting this, high-speed circuits and systems are required. We should be able to handle these high bandwidth applications. And over the decades, VLSI technology has been growing, as we talked about. We are launching this program to generate and upskill the manpower in the semiconductor sector in India. And this program aims to provide students an exposure by making them understand not only the traditional methods of designing, testing, functioning of VLSI circuit systems and their performance assessment, but also to evolve towards embedding how intelligence will be inbuilt going forward in the many of the chips that are coming, and how we will leverage more and more of AI while developing and designing the VLSI systems. More details can be found on our website, and we'll be very, very happy to answer any questions related to any of the members who want to upskill themselves by enrolling to this program. So in AI, two very important concepts that are there. One is on training, other is on inference. By training, we mean that all AI applications must be capable of training and inference. What is their role? During the training phase, developers present images to the neural network. For instance, in a car scenario, maybe any obstacles like of dogs or pedestrians or anything, right? So those kind of training sets are then made available to the neural networks. After the network has viewed billions of images and is fully trained, it is capable of recognizing. So cloud is an ideal location for training. So now we are trying to debate where AI should function more, cloud vis-a-vis on the edge itself. Cloud is an ideal location for training because it provides access to a vast amount of data from multiple servers, and more information that AI application reviews during training, the better its algorithm is. In terms of the inference, AI algorithm handle less data, but they have to generate response more rapidly. For example, car does not have the time to send images to the cloud for processing once it detects an object on the road. Nor do medical applications that evaluate critically ill patients have the leeway when interpreting the brain scans after hemorrhage. And therefore, edge or in-device computing, that is making the decision closer to where it is required, it becomes very, very crucial. And that is the role why we are trying to bring AI to the edge, and we are trying to make different kinds of systems for cloud AI vis-a-vis the edge AI. And when we design semiconductor chips for these different segments, that is for the cloud vis-a-vis for the edge devices, this is something very important consideration point that we need to consider. This slide shows an example use cases of the importance. For example, what kind of systems will be used? If, for example, for a language translation or a speech understanding, we require processing speeds to be great. We require, for example, maybe hardware interfaces to be somewhat. So therefore, GPU or ASICs are getting used for training and inference purposes. If you look, for example, in the route planning or optimization, a GPU may be used more for training. Inference can still perhaps be done by a CPU, which can be a relatively easier and cheaper method, for example, to be deployed at the edge. So in autonomous drivings, we might have ASICs for training, but we can have GPU, ASIC, and FPGA as a combination for autonomous driving. For various aspects and the consideration points that we have in terms of the processing dollars that we are spending, or low cost of development, and so on. So there are companies now, they are finding opportunities in the AI market. There are leaders already emerging. In compute paradigm, for example, opportunities in the existing market are accelerators for parallel processing such as GPUs, FPGA, and also newer opportunities are workload specific AI accelerators. We already have NPUs, for example, available in the market. Many system on chip these days available in the mobile phones, for example, have an NPU that give performance even up to 40 teraflops. In memory, from high bandwidth memory and on-chip memory to evolution as emerging non-volatile memory in the segment, storage space from potential growth in demand for existing storage systems to AI-optimized storage systems and emerging NVM as non-volatile memories as a storage device. In terms of networking, infrastructure for data centers, moving more towards the programmable switches and high-speed interconnects that we are building. So the key consideration points for what we discussed is that high demand of portable electronics, in particular, portable electronics is what is getting deployed at the edge. In recent years have significantly increased the demand for power sensitive designs with sophisticated features. Continuously, we are trying to have device downscaling in the sense of trying to go to higher process nodes, which from 10 nanometer to 5 to 3 and so on. So continuously, we are trying to do that, which is one of the driving force of the IC technology development. Currently, we have already seen announcements, public announcements that 3 nanometer gates all around technology-based devices are getting ready for production. This aggressive downscaling of CMOS technology has created multitude of challenges for design engineers and opportunities. For example, semiconductor complexity, process complexity is increasing as the transistor dimensions are decreasing. They are getting packed more and more close together. What that also means is that simple scaling does not be applicable anymore, because though devices are small, many aspects of their performance deteriorates, like leakage power increases, gain decreases, sensitivity to process variations in the manufacturing increases. The profound increase in the process variation is significantly impacting the circuit operation, leading to variable performance, limited and variable size transistors. This impacts the propagation delay of the circuit, which behaves much more like stochastic random variables and so on. To maintain the performance trend of these VLSI systems, which are handling increasing challenges due to this increased process variability, design complexity, and chip integration, we need to continuously look at having an affordable design for future technologies which are based on advanced design techniques, and therefore the usage of AI and ML tools, for example, to improve the cycle times or turnaround times, and therefore more and more usage of the AI and ML in the electronic design automation tools. AI and ML focuses mostly on learning, reasoning, predicting, and perceiving, and therefore AI and ML can identify trends and patterns in large volumes of data. Therefore, this AI ML algorithms can handle multidimensionality and multivariate data at high computational speeds. Over the last decades, several of these strategies have been extensively applied in the field of VLSI design and technology, and the program at IIT Jodhpur plans to inculcate many of these technologies as we try to look at the next generation VLSI design. From the reference that is provided here is one of the very good paper that I looked at recently. AI for VLSI technology encompasses across architectures for memory systems, algorithm evolution and systolic arrays, in physical design, in terms of placement, routing, clock tree synthesis, for circuit simulation, whether at device level, gate level, circuit level, and post layout, in manufacturing, particularly metrology, in many of the equipment related functions. AI's usage is very, very critical and important so that equipment can run at a very high utilization levels and resulting into a very better yield estimation and better reliability analysis. Whether we perform testing using different methods of verification, the usage of AI and ML leads to much more predictive kind of performance enhancement if we leverage AI for VLSI design technologies. Therefore, not only are we making chips that help into AI-related applications, but the emphasis is also significantly on using AI to improve the VLSI design and the whole of the chip design and manufacturing process. I believe that this slide we discussed in some manner embedded AI versus edge AI. Traditionally, we perform complex AI computations in the cloud with the implementation of AI modules on GPUs and on the session border controllers. There is lesser and lesser dependence on the cloud for the AI data processing, particularly when we need the result of the inference very soon. So there are two different approaches that are possible. Include embedded AI capability in custom SoC. So at the edge device, we try to embed that AI into the device itself, optimizing chips architecture by reducing instruction counts, power consumptions, calculation time, and including embedded AI in internet connected devices, for example, smart camera sensors or in smart medical devices which are deployed at the edge. in this slide, another important trend that we are talking, why the AI in VLSI design and vice versa is getting more and more important. With the IoT, though people have been talking about IoT since last 10 years, it is really picking up now, particularly because of the narrowband IoT and the 5G, which enables massive machine type communications with the low latency paradigms to be built in. There is an explosion now that is likely to happen, and we expect 27 billion connected devices by 2025 across various segments. Again, the goal here is that we want to make these devices which have low power consumption, high battery backup, low cost, faster computational speed, and very short design time. With the explosive growth in the adoption of AI to address a large range of problems that were deemed very difficult, the IT and semiconductor communities are developing computing platforms that provide the desired level at acceptable energy cost. So far, majority of attention, as we discussed, was more directed towards cloud AI, with data being the largest common denominator in creating value for industries, governments, and individuals. However, the quest for intelligence is fast becoming prominent and essential feature at the edge as well. That is where these devices, 27 billion and more counting, where trillions of things will combine together to generate even more data. Given severe constraints that govern edge devices in terms of efficiency, footprint, robustness, and cost, we want to therefore are looking for an innovation across all levels of the stack, from computational concepts the way down to the implementation strategies, to develop products which will range from automotive, mobile, industrial immersion, IoT to wearable and implantable. So, as a trend, cloud versus edge AI and the devices and chips that are getting done in data center at the edge, very rapid shift that has been happening. So in data centers, for example, in inference and training, the trend is getting more and more lesser and lesser of CPU being utilized, and we have more and more GPU and ASICs that is getting deployed in the data centers. And similarly, in the edge architectures, we can see that more and more, for example, of the ASICs that are getting deployed for the training, as well as while for the inference, also we are getting into more and more of ASIC deployment. So the trend and evolution, that is CPUs giving way to more ASICs or FPGAs or GPUs, is across and all prevalent. This is another model. As I mentioned, I encourage all of you, the participants, to look at this international roadmap on devices and systems, published, latest publication is of 2022, published by IEEE. So what it does is that across many sectors, both in the manufacturing side, in the design side, in the application space, it predicts and gives a roadmap on what to expect. So in terms of semiconductor technologies, now what one can see is that post 5G era, the 5G semiconductor chips are already available. We are getting into 6G standard definition. We will get into more and more real-time computing with AI. And therefore, our semiconductor technologies must evolve to embrace more of IoT edge computing, including the interaction between the cyber and physical world, to create ultra low power and energy harvesting techniques, to embed intelligence inference, as we talked about, from sensing the data to abstracting to inference from various actuators that, for example, provide the data to it, across medical healthcare segment, the high-speed networks that we talked about, the data centers that we talked about. So across data centers, which require high-end, high-performance quantum computing as it is coming, to high-speed networks, to the actuators that are sending data, including automotive, to the IoT edge computing, we need to have semiconductor technologies evolve in order to develop systems to cater these kind of requirements. Therefore, while currently we are into 5 nanometer process node, we already have announcements from Samsung of 3 nanometer with gate-all-around technologies. We expect that in the next few years, more and more shrinkage possible. This is a roadmap, and expectation is that by 2030, we may go to 1 nanometer equivalent kind of process. Though logic transition to 3D in the sense of how logic and memory can be stacked together, or how logic can be stacked. So logic transition to 3D is still aimed in 2025. We are continuously evolving in our roadmaps for the newer device structures, from FinFET to logic gate all-around technology, and further in the 3D stack versions. So various foundries in the world, Intel, Samsung, TSMC, global foundries, are actually moving in this direction in the newer and newer generation, leveraging on the EUV technology and going further into these aspects. So I will perhaps the point that I want to mention here is that for semiconductor people, the future is very exciting. In this slide, all I want to highlight is that for cloud computing, latency sensitive processors, we can expect that number of cores per socket go to 896 in the next 15 years or so. Therefore, processor-based frequency, basically this one has to worry about, of course, about the power consumption along with that, is also likely to increase further. Similarly, in the personal augmentation space, where it is a space where a wellness segment, for example, or face recognition segment, for example, these drivers, we are likely to have a significant increase in the GPU and CPU cores. And also the frequency, of course, is going to be relatively around 3.4 gigahertz is where we will operate. Similarly, in the IoT space, we will have CPUs per device also increasing, and also cyber physical systems and interaction between cyber world and the physical world. We expect the number of devices to significantly increase over the next 15 years. An example of this is that the performance of the computation is changing because we are trying to have more and more repeatable software instructions being now built into the hardware. As a hyperscale accelerator example, we are trying to download more and more software into the domain-specific silicon accelerators along with the custom silicons. So these are the new growth drivers for the emerging VLSI systems. I think we have emphasized enough. From data centers, also AI has clearly moved from cloud to the edge, and we are having more and more devices at the edge now. So I come to another important paradigm that is when we say intelligence is moving to the edge and we are having IoT devices, we are in the world of artificial intelligence of things. Means the things that are deployed to the edge will have an intelligence by themselves. That intelligence may be related to recognition, estimation, natural language processing, speech recognition, and so on. Therefore, AIoT is becoming a very, very important consideration area for future growth of semiconductor business and semiconductor technologies. In AIoT architectures, one will have intelligence in the device as well as at the edge. Of course, the cloud intelligence has been there and will continue to be there, but the intelligence is getting more and more downloaded to the device level. It is in this context that AIoT with the edge devices will have significant number of applications across manufacturing, energy, mobility, healthcare, with the advantages of intelligence, efficiency, connectivity, transparency, and various technologies that involve sensors, communication, computing, AI, ML, AR, VR scenarios, and so on. It is in this context IIT Jodhpur is trying to take a significant lead, which I want to highlight. So we can expect that with this AIoT, we will have more than 350 billion devices in the year 2030, where worldwide significant increase of the devices, along with the internet traffic that is going to increase. So there will be demand for higher data rates, which will be coupled, which is, for example, getting fed by the 5G devices and 6G devices coming, which will require significant number of semiconductor content, but also the billions of devices, which will again increase the significant semiconductor content in them. And there are many, many research challenges in the AIoT scenarios. For example, when we have devices deployed at the edge, what is the situational as well as intentional awareness for the AIoT? How the collaboration for communication amongst these billions of devices that we are talking will happen? How AI-enabled IoT operation and the maintenance of these devices is possible? Different simulation tools, methodologies, performance evaluations, novel network and communication protocols, intelligent resource management models. There are a variety of things that are mentioned here. I'll not go to each of them. All I want to highlight is that AIoT itself, both from application, design, and semiconductor perspective, is going to become very, very important as we go ahead. It is in this context that IIT Jodhpur is very happy to say that it is setting up an artificial intelligence of things innovation hub, which is basically an innovation hub, not purely as an academic research. It is to create sustainable and advanced ecosystem with facilities. That means we will have a small fab setup here for end-to-end design, development, prototyping, pilot production of AIoT systems at our technology park. We already have around 16 faculty members and around 50 PhD students working in these areas. And we want to significantly strengthen the AIoT space, including semiconductors, networks, communications, and so on, which is in synergy with India Semiconductor Mission and the new policies that have been launched, both for design-linked incentive schemes as well as for the other incentive schemes. Of course, IIT Jodhpur is not in the space for the silicon fab or display fab, but in terms of a sensor fab, that is what we are looking at across applications, healthcare. So currently we have tied up with few industries and we are looking for more industry partners. So the systems that we develop here are not purely academic. We want to make systems that go into industry as a pilot production and which can be deployed commercially. So the current status is that we have already gotten funding and approval from the Rajasthan government. We are in the process of creating a joint venture company here in IIT Jodhpur and trying to include more partners, industry partners, and also Government of India support through MIT. Reason why I mentioned in this technology seminar here is, while there is a significant process and progress and expectations all around the world, it is the actions that we are taking. Firstly, in terms of setting up the executive MTech program for working professionals to improve the quality and the quantity of the people in this space that we are currently into. Secondly, setting up the facilities which will be of the great practical as well as industrial importance, so that IIT Jodhpur can help India lead into the next generation of semiconductor technologies and the intelligence world that we are in. I think I already talked about this. So thank you very much for listening to me. I hope I could cover, though the subject is very vast, I hope I could cover what we are trying to do, where the industry is moving, where the challenges and opportunities lie, and what specific and concrete actions IIT Jodhpur is taking in order to fulfill India's semiconductor mission, as well as to generate manpower in the country, as well as to generate newer technologies and be a hub for making India a semiconductor power center, a semiconductor superpower in the years to come. Thank you very much for listening to me, and I will look at some questions and answers if they have been put here. Any other questions or answers, I'll be very, very happy to talk.
There are two questions in the Q&A box.
Yes, I am checking. What will be the scalability? First question is from Harsada. What will be the scalability of the nodes across car models and technologies? Will the components need to be customized? I believe in one of the slides I talked about, out of the 3,500 semiconductor components, some will, for example, be a very advanced nodes like 5 nanometer, 3 nanometer, and so on, based on the communication and networking and NPU-related capabilities. While there are many other sensor nodes that we are talking about, may still be in the 130 nanometer or 180 nanometer node. So there will be a different kind of, in order to keep the cost based on the performance criteria, there will be a broad spectrum of components that will be varying from 3 nanometer right up to 180 nanometer. Will the customers need to be, will the components need to be customized? Of course, for some of the important emerging use case applications that are coming and evolving. For example, as we talked about road safety detection in ADAS, for example, level 1, level 2, and as we go higher and higher, we have to look at the collision detection warning systems. We have to look, lane departure warning is of course available. we have to integrate lidars, we have to integrate many of these sensors. So there will be a lot more customization, of course, that will happen. Therefore, both the general purpose as well as the ASICs that will be deployed. So that is the answer to the first question. The second question is, I submitted my application for Executive MTech program in May.
So that it can be handled separately. I mean,
So this also I can give an answer. Currently, the timeline for receiving the applications for Executive MTech program has been extended up to 14th of August. And we expect to start the program in the September timeframe. And we expect to have a first semester completed by end of December, and then we move on from there. So we have extended the application deadline, and we are thrilled to and waiting for starting the program in September of this year. Kindly share your email ID for collaborations. My email ID is very simple: Manoj, M-A-N-O-J, Manoj at iitj.ac.in. Thank you.
Yeah. So, in the interest of time, we move on to. So there's one more question before we move on to Dr. Amandeep. It's on FPGA, and how are we utilizing FPGA on 5G or VRAMs?
So FPGA actually is gaining. So two things are currently happening even in the semiconductor world. Firstly, more and more adoption of open ecosystem, even in semiconductor space, which was very closed. So you see more and more openness, particularly in after the RISC-V becoming more open. FPGAs are also embedding more and more intelligence, and at the edge, for example, many FPGAs are getting used. So FPGA is finding a re-emergence, particularly in that space. And also, as I mentioned, that along with FPGA, the open semiconductor ecosystem, when we talk about open semiconductor ecosystem, it is if semiconductor has been a capital intensive business, which indeed it is in terms of manufacturing. However, in the design, earlier there were many, it was very few companies that were offering, for example, open licenses, like in the open software that we get in the software world. Now there is a more and more emergence of open ecosystem that is also happening in the semiconductor world, which I believe will bring in more and more democratization of the silicon world.
Yeah.
Thank you.
I think we should move on to Dr. Amandeep. The questions to Professor Manoj can be addressed to him via email, or we may have some few minutes at the end of the webinar today.
Thank you, Professor Narayanan. Thank you for giving me the opportunity to talk. Thank you.
Yeah, thank you. So, Dr. Amandeep, you can share your slides.
Thanks a lot, Professor Narayan. So let me share the screen. Please let me know if my screen is visible.
Yeah, perfect. Yeah, we can see your screen.
Yeah, thanks a lot. So in the similar line of thought, our current theme, which is on intelligent Vlsi systems. So I shall be talking about smart camera systems, how the cameras are becoming intelligent in the present world. So the brief contents. So I shall be talking about different camera applications, the introduction and motivation towards intelligent CMOS image sensors, where CMOS image sensor is the key element or the IC which is making a camera system. Then I'll talk about the brief about readout and ADC architectures which are currently being employed, different ADC building blocks. So these are the conventional part that I would like to motivate the audience why people are going towards intelligent image sensors or intelligent cameras. So then I shall talk about on-chip and on-array compression techniques, which are a kind of decision-making elements, making our cameras smart. Then intelligence in CMOS image sensors, how currently we are moving intelligent at the pixel level. Then I'll talk about application areas, which is surveillance and medical devices. I'll also give you a glimpse of programmable camera and then conclude the presentation. So it's well known that cameras are everywhere, starting from your mobile phone and going towards medical devices, your autonomous vehicles. So it's becoming now eye of every object. And the requirement of cameras are also different depending on the applications. Like somewhere I can talk about, or we need to have high dynamic range cameras where you have higher sunlight, you are not able to see the images. And when you talk about the dark light condition where you have no light. So high dynamic range is one of the basic requirement which are also coming in our mobile phones. Then there is a requirement of slow motion camera or the high speed camera. I can also use the term high frame rate camera, where the speed which human beings are not able to see, the cameras can see. So there are other applications like 3D cameras where we want to know the distance of the object. Another high frame rate camera is also shown here. The cameras are also required for various medical applications like bronchoscopy, endoscopy, and others. Giving a quick introduction, the camera system basically consists of a pixel array and followed by the readout circuitry. And there should be vertical and horizontal scanners to read the pixel elements. There should be bias circuitry required to pump the required reference voltages to my readout, which includes your A to D conversions, double sampling circuits, memory elements, etc. We need different kind of amplifiers if the signal strength coming from the pixel is very small. Now, at the left side, I have shown the sequence of images where you can see that how much speed of camera we need. So if we have a balloon filled with the water, and the moment you try to blow that particular balloon, what you will see that the water coming out of the balloon I cannot see as a small elements which one can easily see with the high frame rate images captured in this particular sequence of images. So we see that entire water is coming out of the balloon at the same time, but because our eyes are not able to see the very small motion or very the slow motion in that particular event which is being happening, but yes, the intelligent or you can say high frame rate camera can see those sequence of events. So this is just the example of high frame rate camera that I have shown here. So the basic flow of the camera is shown. You need optics, which is a kind of lens and the illumination source. Then you have an image sensor. So earlier technologies were CCDs based, that is charge coupled devices. Now we are going towards CMOS image sensors, which help us or which provides the flexibility of integration in a single IC. Then you have analog front end, which basically includes your preamplifiers or the low noise amplifiers, followed by the readout circuitry like your A to D converters, because the signal coming from your pixels are analog in nature, which can be interpreted in the voltage or the current domain. You need a kind of digital converters, I mean to say A to D converters, to convert that analog into digital end. Now the digital information I received has to be processed. First of all, those need to be stored in the memory and then for further processing. At the right side, I have shown the internal components to make a camera module. For a camera, as I am saying, that you should have a CMOS image sensor IC. Inside that IC, you have everything starting from the pixels, readout, power management circuitry, your clock circuitry, everything. But you need to provide certain clock signals for your camera module to get an image. So that's why you can see that it's a stacked modules I have shown. You have a bias board, you have a FPGA board required to generate certain clock signals or control signals for your camera for getting an image. Then this is a packaged IC, which is the image sensor IC. Now stacking all together and putting a camera lens, you would be getting a camera module, which we see is everywhere and for many used for many applications. Now, the readout of your camera can be done at different levels. Now, depending on how you want to expect the speed from the camera or which performance you are expecting to get from the camera, based on that, you either do the readout at the chip level, where you read all the pixels of the image sensor. You read it sequentially, one by one. You can so if you have a single readout, what you will see that since one pixel has to be read first by the readout followed by sequence of pixels, it reduces the speed of my camera. But it has an advantage that you have a common readout for all the pixels, so whatever noise coming due to readout, the variations coming, that can be certainly reduced. So next is the column level readout, where what we do that we place the readout in each column so that all the pixels in a given row can be read in parallel. So certainly my speed is definitely increased with column level readout architectures. But yes, we have different readout circuit for each and every pixel in a given row. So you will see that, as we know, we talk about the IC fabrication, we see that none of the none of the readout is similar to the next neighbor. So all the readout circuitry will have some mismatch, some random variations, and that introduced a noise, which we call it here as a fixed pattern noise. So column level readout is certainly better in terms of speed, but it is lagging in terms of fixed pattern noise. Then we have a pixel level architectures where you put readout inside the pixel element itself. Now you can think of the speed, that yes, the speed is even much higher than column level readout because every pixel has its own separate readout. But now, since you are putting your readout inside the pixel, so the effective area occupied by your photodiode reduces, and hence you will have very less information being captured from the scene. The major common element of your readout includes A to D converter, which can be of many types like flash, slope, SAR, cyclic, and sigma delta. Now, depending on the requirement of the camera, again, one should choose the kind of ADC we are looking into. So looking into a very basic flash A to D converter, you see that there are plenty of comparators. Basically, we say we require 2 raised to n minus 1 comparators for n bit conversion. Now, if I want to talk about the A to D conversion having higher resolution, I should be using more number of comparators, which becomes a challenge when I try to use this architecture in the camera. So especially if I talk about column level or pixel level kind of architectures, accommodating bigger circuitry of ADC is a challenge because there are plenty of elements, and these elements itself have lot of mismatch compared to each other. Now, when this ADC is placed inside each pixel or for each column, you will see another additional mismatch coming due to one ADC from the other. The other popular circuit for ADC is slope A to D converter. This is very simple compared to your flash because it requires mainly a comparator element, and the ramp generator can be common for all the A to D slope A to D converters. So you have to manage with only the mismatch coming due to the comparator. So slope ADC is widely used in your current cameras, especially if you talk about mobile phones. No doubt slope ADCs are very slow compared to flash, but in terms of noise and in terms of image quality, you will see that the noise is very, very less when you use slope A to D converter in your either column level or pixel level architectures. Giving a quick overview about SAR architecture, which is very popular. So SAR A to D converter is mainly best in terms of low power, and it is highly recommended for medical devices. The reason being, it has only a one comparator element which consumes power. The rest of the circuitry is a D2A converter, which is already working at the edges, and the consumption is very, very small. So this is becoming a very, you can say, evergreen kind of A to D converter that people are using. And now using the SAR ADC with another kind of architecture, people are also looking towards hybrid A to D converters to get more advantages of SAR combined with the other architecture. So the one of the issue with SAR A to D converter is the binary weighted, or you can say the D2A, C2C or R2R kind of architectures of your D2A converter, which actually occupies area. So one can think of that if we want to go for area efficient and high speed design, we can combine SAR with the say cyclic or slope architectures or others. The other one which I have shown here is a kind of cyclic ADC, which is a special uh, case of your pipeline A to D converter. In your pipeline architecture, you have plenty of stages depending on the resolution required, but here we use a single stage and try to reuse a single stage for n number of cycles. So the advantage of cyclic is that it is area efficient, and it is also having higher speed, or you can say almost equivalent to SAR. And so if I compare the different architectures of ADC, we can conclude, like if I want to go for higher speed and area efficient architecture, one should prefer cyclic A to D converter. If one wants to have high speed, low power and low noise kind of architecture, one should go for SAR ADC and so on. So these are the conventional readout which I have talked about as of now. Now the major thing which I will be talking here is like the intelligence, how the cameras are becoming smarter in the current scenarios. So far of our discussion, what I have said, that we have a pixel array and all the pixels we are going to read either sequentially using chip level readout, or in a parallel readout using column architecture, or inside the pixel. But we are definitely reading all the pixels, and that's how our conventional cameras work. We are reading all the pixels, and hence we are spending a lot of power to read all the pixels. But if we talk about the nature scene or the natural scenes, you will see that there are many pixels which are almost having the similar information. Now, the on-chip compression deals with that. It helps us in reducing the number of redundant pixels, and we only read those pixels which are having the useful information. Like the example which I have given is on-chip compression. So we can look into a series of pixels in a given row, and we can see that if there is a substantial change happened or observed in the pixel, then only I will read that pixel. Otherwise, I will just skip that pixel, and during the image reconstruction, I can just either copy that pixel with the previous pixel value, or I can do certain kind of interpolation to have a better quality image. So this is a one kind of intelligence that we can incorporate by skipping majority of the pixels and reading only few. So one of the so you can see here, if you try to skip the pixels, you will see certain kind of streaks, line streaks are observing in figure A, and similarly in figure B you can see the vertical streaks. But if we do the averaging, and the figure C and D of the figure 3C and D gives you an estimate of a reconstructed image, where you can see that if I do the averaging or interpolation, I can have a better image compared to if I just do the copying of the pixels. So these are the different reconstructed images. But yes, what we have done at the IC level or at the image sensor level, what we have done is we have read only very few number of pixels and doing the reconstruction at the off chip or at the later end. So certainly the circuitry can be designed on chip also, because interpolation is a very simple circuit, and similarly copying of element is also a very simple circuit that can be easily synthesized on your same integrated circuit. So the major advantage what we will obtain is your camera would be having a better battery life, because you are not reading all the pixels of a given camera. So the another area where people have started working on is to put intelligence inside the pixel itself. So if you look into the figure A, what you can see that the conventional image sensor having the pixel array, which is being read by your A to D converter. Now, once you have read all the pixels of a given image, you transfer that image and do certain kind of digital processing using a separate, you can say, digital signal processor. So suppose you are interested in motion extraction or detection or object detection kind of algorithms. We are first getting the image, entire image from the image sensor, and then we are doing processing off chip, right? So, but if you look into pixel B, the circuitry B, what you can do, you can design some pixels in a smarter way, which can store the information of one frame with respect to other. So when I talk about the video, we talk about multiple frames. So if I have a circuitry which could be a very small circuit, suppose it could be a very small capacitor element which is going to store the difference of the two frames, and if that difference is good enough, then only I will be reading through the ADC. So looking into figure B, you can see that processing can be done inside the pixel itself, and the pixel will decide, the circuitry will decide whether you have to read that pixel or not. So you are making that decision inside the image sensor itself, and then you can directly get the information. So these kind of cameras are very much application specific for what objective you want to design such cameras. So another example which I have shown it here is a surveillance camera. So we can have image sensor and AI accelerator in a single IC. Now AI accelerator can do a very crude job, you can say, because when we talk about on-chip accelerator, the accelerator also occupies area as well as power, right? So AI accelerator could be a very small AI chip which can do a very basic job of, say, human recognition or object recognition. Once the object is detected, the information is sent so you can say that AI accelerator and image sensor processing is happening at the edge. Once the object has been detected, you can send it to cloud, or you can say a server, to do further analysis. Suppose you want to know what the minute details of the object, so that processing can be done at the cloud, and hence it can be fed back, and accordingly the camera could be used for surveillance applications, where you can say like CCTV camera, if I talk about, which is continuously capturing the scenes. Might be if there is no vehicle coming, or suppose I have put a surveillance camera at my home and I want to just take care of the security, and nothing is happening in the room, why I want my CCTV camera to continuously capture the images? It should be smart enough that if the camera sends some kind of interference or some kind of signal coming due to the change in the scene, only at that point your camera should be able to capture the image. So such kind of examples could be that you can say the emerging field in this area where people are making the camera smart. The other example which I have given here is a wide dynamic range image sensor, which is a kind of increasing the strength of the signal both at the lower end as well as the highlight condition. So especially when we talk about the medical devices, we need an image which should be of good quality. Now, in order to get the good quality image, you should do certain processing inside the pixel. So there are different topologies like logarithmic pixels, linear logarithmic pixel combinations are there, which can be designed to get a high dynamic range. So if you have a low light or if you have a high light, the combination of linear log will help you to get a better scene. So the another example of intelligent camera, the one which I am showing here, is a kind of programmable camera. So this camera is such that it will see whether there is an event happening, and if yes, if event or some changes in the scene has happened, that only then the camera will be reading the entire pixels. So what we can say that by default the camera could be operated in a low resolution mode. Suppose I have a 16 megapixel camera and I don't want to read entire 16 megapixels because I have to spend a lot of readout power. So what we can do is by default, I can use my camera with low resolution, say 1 megapixel. And once if I have detected certain kind of event or some object has been detected, then I can provide a feedback to my camera so that it should read the entire pixels or the pixels in a given area of interest. So that is again another algorithm which we can add on to make the camera smart. That the one common way is just increase the resolution from 1 mega to 16 mega if the object is detected. The other possibility is increase the resolution only in the region where you are finding the object. So such kind of image you can see here. So by default, if nothing is happening, you can see that images are captured in the by default mode, which is the low resolution. But once there is an object, you see that I am only in, because I am only interested in the object, and suppose the object is a human being, then the camera will read only the part of image with high resolution, and rest of the part of the image we are not interested in because we don't have the object lying there. So this is the, you can say, in the object detection mode, and by default, because I want to save power, then it can run in the low resolution mode. So in conclusion, I would say that conventional image sensors are power hungry because they are not smart. But yes, the trending image sensors with on-chip application specific processing are intelligent. This field is rapidly moving towards smart image sensors because people are now interested in having multiple applications of cameras with given specifications. The on-chip near sensor or in-sensor intelligence is becoming a reality now. Now, in future, we would see complex tasks being processed inside the sensor like object tracking. So thanks a lot for listening to me. So I am happy to answer queries.
Yeah. So thank you, Dr. Amandeep. So there were a couple of requests for your contacts. You can, both the email addresses of today's speakers are available. It's there on Google and also IIT Jodhpur websites, EE department. It's quite easy to find. But Dr. Amandeep, any other contacts, information you want to keep so that people can reach out to you?
Yeah, so I can provide the email ID, which is my email ID is also very simple. It's Amandeep Kaur, AMANDEEPKAUR @iitj.ac.in.
Yeah. So we have a question, technical question, which has come. How much of work and importance does an FPGA have in camera system? what kind of compression techniques are used in image compression? Would techniques like compressed sensing would be useful? Are there any other techniques in PIS? There is also the last question of, are these CMOS image sensors primarily analog due to low power advantages, or are there any digital counterparts?
Okay. So first of all, how much of work and importance does an FPGA have? So certainly when I talk about AI accelerator, it's a kind of processor. So your FPGA also have a kind of processing element. So definitely when we try to make certain kind of decision making part, I mean to say the intelligent part, the FPGA can help you in the preliminary level of you can say work where you can do the prototyping. You have suppose the camera module ready with you, and you can do certain algorithms, suppose object detection or image classification preliminary using FPGA. But if you want to make it smaller in size and want to fit it in some place, suppose I want to place my camera for surveillance, for traffic light control, I can't keep my FPGA board there, right? So you want a chip which should do all kind of things. So the FPGA could be used for the preliminary set of work where you can explore the different algorithms. You can understand the, you can say, performance of those algorithms. But yes, in the end, once you synthesize your, you can say, once you synthesize it in the form of your digital counterpart, you can also integrate it in terms of your digital integrated circuit. You can accommodate it with your image sensor IC. So certainly FPGA, I would say, this could be a preliminary level of work that you can try with. But yes, the main thing which could be useful is an integrated system.
So we have a question from a DAE lab, the atomic energy, where they work in, I think, radiation environments. And the CMOS, I think noisy, or maybe actually it can get damaged also, I think, under radiation environment.
So frankly speaking, I have not worked with radiation environments. So I would not like to give any ambiguous answer. But yes, the image sensors that we are designing is not sustainable for high radiations. So there must be separate kind of photo element which we need to take care, because the simple photodiode that we use in our visible light, you can say, region of your cameras, that might not work with high radiation environments.
So having said this, if there are specific problems that DAE has, then we can discuss together to see if we can really find a solution, and based upon that we can move forward.
Yeah.
And so I had some general questions, from a research again point of view. In biology, life cell imaging, sometimes you need very high frame rates and high resolutions in a random manner, so that you can have a manageable data at the same time. You can get very useful information. So that's a slow process, but people take data over several, minutes to hours, and then something happens where you would like to see at very high resolution and at high frames, so that you come to know some processes very deeply.
So basically, when we try to combine high resolution and high frame rate, one thing is very clear: if you have more pixels, you will be spending more time to read, right? So getting high resolution plus high frame rate is certainly a big task. But yes, with the image sensors having pixel level architectures, you can accommodate that, or with column level, you can accommodate that. Now, depending on how much high speed we are interested in, suppose what we have recently designed is 1 megapixel camera which can run with 1000 frames per second. Okay, so now 1000 frame is certainly very high frame rate. But medical devices, we might be happy with 30 frame. But yes, in order to track certain biological movements, we might be interested in higher frame rate. But here we can have again a smart camera where we can by default operate the camera in a low resolution so that speed automatically increases. And once we identify the region of interest, then tune the camera to high resolution mode so that you can take care of the resolution as well as the speed.
Okay. So there is one question which I haven't fully understood, but it is asking whether you can have solutions via hardware improvements or software, something to that line.
Yeah, so definitely when I talk about hardware implementation, it must be more smarter because our IC is a smart one which can make the decision by itself. Now, if you want to go for software kind of solutions, like the example which I have given, like AI accelerator, which I tried to show it in one of the slides, where AI accelerator is placed inside the integrated circuit, making a single IC. Now that AI accelerator can help you in, you can say, crude kind of information, like say object detection. But the detailed thing, if you try to put it in the hardware, it could be more complex hardware, which people might not be interested in, because again, we are also increasing the power of AI accelerator if I want to save something. So the doing preliminary task at the edge level or at the hardware level should be a better solution, and getting more detailed information, we can't get rid of the software, because if you actually see the raw image coming from the camera, people are not at all interested in looking onto those raw images. So without processing, without software, we can't get a high quality image. So that is always an inherent thing we assume to get a high quality images.
Okay, very good. So, Professor Manoj Choudhary, there was a question related to requirement for the VLSI course. Where you expect a double degree, or is it fresh?
So maybe Amandeep can clarify. My understanding is that the related background has to be there, in the sense of all those courses have been done, whether it is EC, CS. I think it's a broad one. Maybe Amandeep can clarify. But I think the related foundational courses should have been done. That is also very, very important. Amandeep, can you clarify?
Yeah, so I completely agree with Professor Manoj. So the students or candidates enrolling for this program should have basics of electronics, because electronics people have read in their first year common course as well, when they must have done their BTech. So this is a specialized course, because MTech is now more towards intelligent VLSI. If you have a preliminary knowledge or the basic knowledge of your electronics and the circuits, then you must be able to cover up this course when you try to enroll for this program.
Okay. So with that, I think we come to the conclusion for today's very stimulating webinar. The first experience in the morning webinar is extremely encouraging. I personally am a morning person, so it's I find my receptive power is much better in the morning. So thank you for a very wonderful session, both Professor Manoj Choudhary and Dr. Amandeep. I'm sure you will get some follow-up questions, and I mean, so we'll be in touch in terms of IIT ACB programs, or if something jointly can be done. Dr. Sushila will definitely follow up. She's unfortunately not here, but I see a great opening and a great topic for interacting with IIT Jodhpur in this very important area for our country. And so my best wishes, and we look forward to having a constant engagement with IIT Jodhpur. And with that, we conclude today's talk. There are some more questions in the box, which are actually agreeing with what I just said. And so please get in touch with the speakers today for any other specific questions, and they'll be very happy to address it. Okay. So again, thank you very much, and we close this webinar for today. Thank you.
Thank you. Thank you so much for providing us the opportunity to be able to talk to a varied audience. And as intended, we try to keep it broad and try to talk more about why it is relevant in today's context and what all opportunities lie before all of us to make India self-reliant in this important space. Yeah, thank you, sir. Thank you so much from my side. Amandeep, maybe.